The future of AI doesn't run on lines of code, but on circuits that fire like real brain cells. Neural networks were inspired by how the brain works. But neuromorphic computing goes further. It is designed to look and act like the brain itself. One mimics intelligence, the other embodies it. This is not just about machines learning, it's about machines thinking like us and maybe even becoming us. What is a neural network? Neural networks are the reason AI can recognize your face, write text, or even generate music. Neural networks are algorithms inspired by how our brains work. But they are just math. They consist of layers of neurons connected by weights. Input layer, hidden layer, and an output layer. Each connection has a weight, and learning means adjusting those weights based on data. For example, image classification, ChatGPT predicting stock prices. These models run on traditional digital computers using GPUs or TPUs. But what is neuromorphic computing? What if computers literally work like brains with spikes, synapses, and neurons firing together? Neuromorphic computing is a hardware based approach that mimics the actual biology of the brain. Instead of running code, the chips behave like neurons, sending electrical signals called spikes. Let's see some features of neuromorphic computing: event based computation, low energy usage, parallel and asynchronous communication. For example, Intel's Loihi and IBM's True North use neuromorphic computing. These chips aim to replicate how the brain processes data. How neural networks work under the hood. Let's peel back the layers and see how neural networks actually learn and make decisions. It's not magic, it's math. Neural networks use matrix multiplication and back propagation to learn. They learn by doing lots of math, multiplying numbers in layers called matrices and adjusting their guesses using an algorithm called back propagation. They are trained using labeled data. We feed them examples with known answers like images of cats labeled cat so they can learn to match patterns to labels. They need large data sets and powerful GPUs to work well. The more examples we give, the better they learn. But all that training takes a lot of computing power, which is why we use GPUs. Neural networks learn in batches, not one example at a time. They process data in chunks, like 32 or 64 images at a time, which helps them learn faster and more efficiently. Training them takes a lot of memory and computing resources. Because of all the layers, weights, and data, they can easily fill up your RAM or crash your computer if it's not powerful enough. Usually, the more data you give, the better the model performs. Feeding it more examples helps the network generalize better, but only if the data is good and diverse. How neuromorphic computing works. Imagine a brain made of silicon, not code. That's what neuromorphic chips are aiming for. This is a chip that makes neuromorphic computing works to mimic how our brains think using hardware. Neuromorphic chips use spiking neural networks or SNNs. Unlike traditional neural networks, they use special models where neurons send signals as spikes, short bursts of electricity, just like in the human brain. Each neuron fires only when it's needed. It's event driven. Neurons don't keep running all the time. They activate only when something important happens, saving energy and improving performance. They process information over time just like real neurons. These chips understand the timing of signals, which helps them learn patterns in sound, motion, or anything that changes over time. Neuromorphic chips are extremely energy efficient because they don't compute constantly and mimic the brain's natural flow. They use far less power than regular chips or GPUs. They perform well even with noisy or messy data, just like our brains can recognize a friend's face in a blurry photo. These chips can handle unpredictable real world information better. Intel's Loihi chip has 130,000 neurons, 130 million synapses. That's massive brain like structure packed into a tiny chip, capable of learning, adapting, and solving problems on its own. Here's what separates artificial brains from mathematical models pretending to be brains. Neural networks are inspired by how the brain works, but only in software. Neuromorphic computing, on the other hand, is built to physically mimic the brain structure using hardware. Neural networks require a lot of power to train and run. Neuromorphic chips use ultra low power by firing only when needed. Neural networks don't work in real time, they process in batches. Neuromorphic chips can respond instantly using event driven signals. Neural networks typically run on CPUs and GPUs, standard computing hardware. Neuromorphic systems need specialized chips designed to mimic brain activity. Neural networks are highly developed and widely used in AI today. Neuromorphic computing is still emerging and experimental. Neural networks learn using backpropagation, a method that adjusts weights based on error. Neuromorphic chips learn using Hebbian learning or spike timing dependent plasticity, just like real neurons. Where do we actually use these technologies today? Neural networks are used in generative AI's applications like ChatGPT, DAL-E for image creation, medical imaging, fraud detection, and autonomous cars for perception purpose. And neuromorphic computing at its basic stage is used in robotics, low power edge devices, hearing aids, brain machine interfaces, and sensory systems. If neuromorphic computing is so powerful, why isn't everyone using it yet? Lack of programming tools. Traditional coding languages are not designed for brain inspired chips, making development tricky and unintuitive. Hard to train SNNs, spiking neural networks. Unlike regular neural networks, spiking neural networks are biologically realistic but mathematically complex and hard to optimize. Fewer researchers and less support. Only a small community is working on it, so resources, documentation, and shared breakthroughs are limited. It is still experimental. Most neuromorphic systems are in labs, not industry. They are not ready for mass production or real world deployment. It needs a shift in software or hardware design. To go mainstream, you need to rethink everything from operating system to chips, and that is a massive transformation. Will neuromorphic computing and neural networks compete or team up? Neuromorphic is future ready. It is energy efficient, real time, and adaptive like a brain. Neural networks are today's power. They are fast, reliable, and backed by massive tools and ecosystem. Hybrid is likely. The future may blend both, using each where it works best. Neuromorphic's role. It may drive the next wave of edge AI, wearables, and smart robotics. You now know the key difference between simulating the brain and actually mimicking how it works. Thanks for watching. Let me know in the comments, do you think the future of AI is neuromorphic, neural, or both? See you soon in the next video. Bye for now.